X10 computation of potential energy. This is the gravitational force. We have a capital M placed at the origin and small m is placed at here, whose position vector is given like that. You find it is proportional to negative. The reason is that we assume that this force is applied to small m instead of capital M. They are, according to Newton's third law, that is the law of action and reaction, their directions are opposite, equal in magnitude, and direction is opposite. And gravitational forces, Newton's universal gravitational force is always attractive. There is no repulsive force, and therefore we have negative sign on it. And proportional to the strength is proportional to the product and universal constant called gravitational constant. And then this is x vector divided by the cube of the magnitude. And we recall that x vector divided by its magnitude is the unit radial vector. Therefore, we have canceled the one single magnitude r, and we arrive at the vector 1 over r squared, and this unit radial vector represents the unit length, and the direction is from the capital M to the small m. The negative sign indicates that the gravitational force is pulling this small m to capital M. That is the attractive force. What is the question? Discuss how to determine the sign of the work done by the gravitational force to bring a massive particle from infinity to a certain finite distance from another massive particle. Okay, we have m at infinity, and we have capital M, and we brought this small m along an arbitrary path to here. By the way, the work done by the force that we are interested in, gravitational force is pulling. We remember the gravitational force is always along the radial direction. Aha, if I move this, for example, I can follow simplest path. This, for example, this path and this path. That's fine. And in here, unit radial vector is along this direction, and our displacement dx is along this direction. And is it repulsive or attractive? It is attractive force. This force is parallel to the opposite direction, to the radial direction. So anyway, f and dx from the infinity to a finite position along this path, they are parallel. Work done by the gravitational force from infinity to here is positive. And then we'd like to rotate from here with the same magnitude, x magnitude, that is the radius, tangential direction. If the displacement from here to there is perpendicular to the radial direction, the displacement and the force, they are making right angle. Attractive force and displacement, they are making a right angle. So during this displacement, we do not have any contribution, vanishing. Only the radial direction opposite toward the center. This is working. So work is a positive, positive. Gravitational force does work positive way. In that case, we remember work replacement with the minus potential in the work kinetic energy theorem. Replace this one negative. So the work from infinity to here was a positive. Therefore, the potential energy has decreased. Decreased. Very, very important. Whatever amount you compute, you don't forget about the sign. At the end of the day, you don't, if you forget about the sign, you have completely wrong answer. Keep in mind. Gravitational potential energy between 2 point masses, 1 and 2. Okay, we know what it is. The distance we here, this guy was at the origin. What is that? X vector minus 0 vector absolute value. However, if we have M1 and M2 in different places, origin is somewhere around here at X1 and X2. Potential energy depends on their distance. There's nothing to do with their distance from the origin. This origin is just unimportant. Physical one is just distance between these two masses. Therefore, our formula is identical to this, except that we have replaced capital M with M1, small m with M2. X is actually X minus 0, so I revive the subscript. So replace X with X1 and 0 with X2, something like that. What happens if I have three massive particles? It's not complicated because first I have M1. There is no need to work if there is nothing around it. After that, I bring M2 from infinity to there. Okay, so the amount of work I require is positive something. And I just put negative sign on it to find out the potential energy of this two-body system. And that is this. We know this very well. And let's bring another mass from another infinity to here. To bring this, we have superposition principle. Superposition principle. Okay, mathematician says and you can add numbers algebraically, and they only add algebraically will define quantity. Physicists must test whether we can apply mathematics or not. That's quite important. That is absolutely different from physics and mathematics. When you compute something, you need to determine whether it can be computed or not. In mathematics, you can do always well-defined thing because mathematics is nothing to do with nature. They copied nature and that they created their own world. Mathematics is nothing to do with the physical nature. They never fail. However, we need to consider what's going on. And in some case, we can make a mistake. And if we make a mistake, we need to correct. Okay, we have two things. And if I bring the third mass to here, there will be a gravitational interaction between 1 and 3. And there is another gravitational interaction between 3 and 1. However, we assume that these 1 and 2 do not interfere their interaction with the other. Strange, but it has not been disproved yet. Not been disproved yet. That means it is not perfect, but we believe it seems to be correct. It seems to be correct. So that is a postulate of a superposition. In mathematics, they claim it is axiom, and that axiom never fails. But in physics, this kind of superposition principle is believed to be correct, but we do not declare it is given by God, for example. We don't know what, what reality is. Okay, wait a second. Assuming the superposition principle, I can bring this one to here. Then, finally, the interaction between 1 and 2 doesn't change. 1 and 2 doesn't change. However, if I bring this the third one in here, new interaction between 1 and 3 and 2 and 3 appears. This is the final result. So you have found that they're all possible combination. It's not a permutation, combination, because two objects, they have a potential energy. We do not have a difference between 1 and 2 and 2 and 1. They can exchange the order. So this is combination instead of permutation. Permutation is a 6. There we only have 3 terms instead of 6 terms. That is important. Number 3, distribution of mass over finite space V is given by the mass density, okay, the unit volume. We assume that the distribution is fixed. What is the work done by the gravitational force between this fixed distribution and a point mass? Okay, so we began with a point-point interaction, capital M, small m. And then we considered the three-body interaction, M1, M2, and M3. Okay, in that case, I have a single point mass, and then collection of mass is a larger mass. And I can even extend this one. This is just like a sun, a very large object. Okay, in that case, I can make use of the previous result. First of all, point-like approximation, and then bring many things and sum them all. Superposition principle. So these two ideas is applied, these ideas apply to compute the interaction between the sun and Earth, or Earth and us. Something like that. Okay. Our strategy is to apply these two previous results to compute the large scale mass distribution and the point mass, the gravitational interaction. First, density is mass per volume. d cubed y represents the volume. The mass distribution due to this small mass at point y, we have origin and we have y. Y varies inside this volume, and we have a very tiny small m at x. And what is the distance between them? We have y, so I have x. Distance is x vector subtracted by y vector magnitude. I have replaced this capital M with the dm. It used to be x in the point case. It used to be, this one is a 0 vector and x, so I have replaced this one with y, and difference is x minus y. Magnitude q, that is x minus y, absolute value q. All right, and then replace this mass by density multiplied by volume. Density multiplied by volume. I need to integrate over this mass distribution, whatever it is. It can be an Earth, it can be a sun, or a galaxy, or something like that. So integral, and substitute this guy in here. So carbon copy, and then I have substituted in here the work done by the gravitational force to displace mass m from infinity to this place. You can follow this calculation, but I can always copy previous result. This is for the point mass m and point mass capital M. Okay. Point mass rho d cube y. This is point mass. So what I have done is just to attach it the integral sign. So all the details calculation agree with the previous one. So application. I'd like to compute the gravitational force or gravitational potential energy due to a uniform mass distribution over a circular mass distribution. And to simplify our analysis, we will allow this small m to move around a z-axis only. And this is a cross-sectional view, so this is on the xy plane. And these are mass. By the way, we can apply the previous method. All of the points, these points, we can identify this point by y. Because this is a z-axis, we are on xy plane. Radius r. Okay, what's that? This is E theta in the two-dimensional plane. E1 cosine, E2 sine. Okay. And what is x? X is the position of the point mass. Position of the point mass, well, is it this one? Okay, substitute this one in here. Distance between these two. Point mass small m and the capital M. By the way, this constructs a cone, and any point on the bottom has equal distance. That's the reason why we have chosen the z-axis. If it were here, it was rather complicated, but we have chosen the x direction. So from a given point, the distance between this small mass m and any part of this circle, they are always the same, independent of theta. And we can draw a right triangle, radius r, this distance is z, and middle school student can say this is square root r squared z squared. Okay, that's fine. And then we carry out the integral. Density, this is a capital M distributed over 2 pi azimuthal angle. Integration over, by the way, this integration is a trivial. This one is independent. Integrand is independent of theta. It is just a simple multiplication. So finally, what I have found is the distance from any point to this small mass is constant, and potential energy is completely determined as this. And using that one, I can apply minus gradient. This is a potential energy potential energy, and we have negative gradient, but negative gradient is a negative of E1 x derivative, y derivative, z derivative. What we have is only z dependence. X, y component completely vanish, and only the z component survive. And what we have to do is nothing but the z derivative of this potential energy and attach a negative sign on it. Minus minus becomes a plus, and we take the derivative of this. And the chain rule is applied again to find out the final answer. As a result, the gravitational force applied to a mass on the z-axis is attractive. Why? This z is a positive, and toward this, z is negative toward this. So because of the gravitational force is attractive, so haha, it seems to be oscillating. Unless its kinetic energy is very large, it is trapped somewhere around here and oscillate. Consider particle with mass m. Okay, we know the curve of force is 0 for the gravitational force. That it is approved in the X9. I extend, so you don't have to worry about it. It is a conservative. Gravitational force is conservative. So because it is irrotational, after dx arbitrary closed path, this work is a 0. Okay, what's that? This is conservative force. If it is conservative force, there is a potential energy whose negative gradient is force. That is what we have already shown. So we have already made use of potential energy. That means that the reason is that this force is conservative. We made use of the fact that gravitational force is conservative. So because the gravitational force is conservative, the total mechanical energy is T plus U, that is constant. So what we have is a sum of kinetic energy and potential energy is invariant, independent of time. You can apply the binomial expansion for a special case when z is a very small or whatever limit. You in the you can take the limit to find out that I told you it may be oscillating unless the kinetic energy is too large. In fact, it has indeed showing uniform circular uniform not a uniform circular motion, simple harmonic motion in the limit, some limit. So you will study based on the questions. That is a checkpoint file.